So 3.8 is going to be another application basically on exponential growth and decay. So exponential growth and decay, any model where the rate of growth is proportional to the actual amount. So examples are population, half-life, and compound interest. We'll probably do the most with population. So basic idea, the more people there are, the faster the rate of growth is going to be. The less people there are, the rate is going to be slower. Okay, the bigger the population, it's going to grow even faster. Think about an exponential curve. As x gets bigger, the rate of growth also increases. Same thing the other way. As x gets smaller, the rate of growth is smaller. So the two have to do with each other. So very simple, that's what this is saying. dy dt, remember, is just the derivative equals k times y. This is considered a differential equation because it involves an unknown function and its derivative. So dy dt is the derivative. Y is the actual y value, like how many people there are in the population. And k is some number. K is just a constant. K is called your constant. Okay, if k is greater than 0, it's growing. Less than 0, it's decaying. We're going to talk about the solutions to this equation. Always look like this. Y of t equals y sub 0 times e to the kt. You have seen this before. I'm sure you all remember. If I wrote it like this, p e to the rt, you'd go, oh yeah, it's the same thing. Okay, it's the same equation where y sub 0 is how many you begin with. Okay, in this case, this was how much money you started with. And then e is e. K, I'm calling, is the rate where it used to be r. T is time. And then I'm saying y of t instead of a. So you've seen this before. Now, if you just differentiate this, you find the derivative of this equation right here. You're going to get k times c e to the kt, which is just k times y of t. So basically, this is just the derivative of this. Okay, why is there a y in it? Because what ends up happening is you end up with k times the original equation, this. So instead of writing this whole thing, we're just writing y, which really stands for the y value. So you're going to be asked to do a couple different things. You're going to have to basically just know those equations. But you've seen that rate of growth equation so much that I kind of think it's easy, even if you just remember the PERT model and apply it to what we're talking about. So you could read the first problem. It's telling you the population in 1950 and then again in 1960. And the first thing we want to do is find the relative growth rate. Okay, so in order to do this, I need to actually get my the k value. Okay, so however I think about the equation, y of t equals y sub 0 times e to the kt. So it's telling me I'm starting with, I'm going to call my starting value, my p of 0, population at 0, is 2560. And 10 years later, it's 3040. I'm going to do it in millions, okay? So now I can use this to set up your equation. So I know that to start with, I had 2,560 million times e to the k, and I'm going to say 10 years later, this is going to equal 3,040 million. Okay, and now if I solve this, I can get my k value. Okay, so divide both sides by 2,560. I don't think I need to do this algebra. Some of you are going to say, how did I get that? And then I would take natural log of both sides, and then I would divide by 10, and I get 0.017185. Okay, so that is my growth rate. So in terms of a percentage, it would be 1.7%. So it's growing at the population is growing at 1.7%. Okay, so what would the actual original equation be? Y of t, or I'm going to call this p of t, equals how many I started with times e to the k, which is the 0.017 t. So there's the equation I could now use to find any amount. And then it's not asking for it, but my derivative equation would be dp dt, or p prime, would equal the relative growth rate, 0.017, times p, where that's your y value. So there's really the two equations I can get from all that information. And then it says use it to estimate 1993 and 2020. So in order to estimate the world population in these years, I would use this equation. This is going to give me the rate of the population, dPdt. This is just going to give me how many. So in order to find 1993, I would just plug in, figure out what year that would go with. So if I called 0 my 1950, then 1993 would be 43 years later. So to figure out 1993, I would plug 43 in. And then for 2020, I would plug 70 in. I think you're following this. This is the hard part, is figuring out these two equations and then understanding which one to use to answer the questions. Okay. So let's try to do one more. I think I have two more. Okay, another one. I divide into 2 cells every 20 minutes. So it's telling me that it divides every 20 minutes. And the initial is 60. So you start with 60. And then in 20 minutes, I'm going to divide into 2. So I'm going to double basically. Okay, so my original, how many I'm starting with, my P of 0, I can say, is 60. And then 20 minutes later, which I'm going to call 1/3 of an hour because I'm in hours. So P of 1/3 is going to be what? It's going to double every 20 minutes, so 120. So that information is really, again, giving me 2 points. I just have to kind of dissect it and say, what does it mean? And then you're being asked to do the exact same thing. So now I would set up, I'd say 120 is going to equal 60 times e to the k times 1/3. Exactly like the last problem to get my k. Divide both sides by 60. Okay, so I'd have e to the k times 1/3 equals 2. Take natural log of both sides and multiply by 3. So my answer would be 3 times natural log of 2, which I could be fancy and I could make the 3 be the exponent. So this is really natural log of 2 cubed, which is natural log of 8, which I could get a decimal or I could leave like that. Doesn't matter. Okay. So for part B, so there's my k value, natural log of 8. You could get the decimal, but there it is. The number of cells after t hours, that's just the equation. So now what would the actual function be? The number of cells, I'm calling P of t, it could be y of t, doesn't matter, guys, what I call it. I'll call it y of t because it's not population. Okay, so y of t, number of cells equals how many I start with, times e to the k, which we just found to be natural log of 8, t. There's my function. Okay. The rate of growth function would be what? dy dt, the derivative, would equal k, which is natural log of 8, times the y value, times y. Okay. Part C, find the number of cells after 8 hours. So I would use this function. This is how many I have. This is the rate at which they're growing. So I would use this function and I would just plug in 8. To find the number of cells, and I think you get a very large number, so I would have 60 times e to the natural log of 8 times 8 hours. Okay, and I don't think I wrote the actual answer, but you see what you're doing. Okay, and then finally it's actually the next question's asking find the rate of growth after 8 hours. So this is talking about my derivative, my rate. This is just talking about how many. So I use the original. So finally, this one, I would use my dy dt equation, which dy dt equaled natural log of 8 times the y value. Okay, so after 8 hours, now here's the tricky part. I'm not plugging 8 in for y. I have to plug how many there were after 8 hours, which is the answer to C. Okay, so because my rate of growth after 8 hours would be the natural log of 8 times the y value of 8. So this is really y of 8 that's going there, which is the answer from C. Okay, so I would have the natural log of 8 times the answer from C, which I think is, I just did 1,006,632, 960. And if I multiply that, I think you get like 2.093 billion for this answer. This is 0.3 billion cells per year. Okay. So again, the only time you're going to use the derivative equation is rate of growth. For the number of how many people are in the population, I would use the original, just the y of t equals how many I start with times e to the kt. So it's really just knowing which one to use. And then e, when will I reach 20,000? I would use the original. So I would say 20,000 equals 60 times e to the natural log of 8 times t, and solve for t. So do some algebra, divide by 60, divide both sides by 60, take the natural log of both sides, and this comes out to be 2.79 hours. I'm trusting that you could do this algebra from last year. It's really just solving an exponential equation. See, that's why we do all this stuff. And then I think I have one more problem. So the last, I talk about radioactive decay. Really the only, only difference is now K is going to be negative. If you look, it's exactly the same. I'm using M. It's still how many I start with times e to the kt. K is still going to be your rate, but now it's going to be negative because I'm decaying. So nothing is really different in a problem like this, except I have a negative value. If you read the first one, the half-life is 1,590 years. So that's how long it takes for this sample to be cut in half. Okay, so a sample, I start with 100 milligrams. Find a formula for the mass that remains after t years. So again, if you just, every problem, you could start with 2 points. You know you're starting with 100, so I'll use M for this problem. I hope you realize it's all the same. It doesn't matter what variable I use. Okay, so if M of 0 is 100, starting with 100, and then after what it says, it takes 1,590 years to be cut in half. So without 1,590 years later, I would have 50 milligrams. Okay, so there's your 2 points. You're doing the exact same thing. Plug it into the equation. So I'd have 50 equals 100, how many I start with, times e to the k times time, which is 1,590. That's going to give me my k value. If I solve this, I get negative natural log of 2 over 1,590. I left it exact. And then I could, so then what would your equation be? M of t equals how many I start with times e to that negative natural log of 2. Not very pretty, 1590 times t. They're all the same. Part B, find the mass, so how much you have after 1,000 years. So now I would just plug 1,000 into this. So I would just do M of 1,000 to see how much I have after 1,000 years, and it's 65 milligrams. Okay. And then the last question is asking, when will the mass be reduced to 30? So none of these questions are asking for rate of growth of the mass, or I'm sorry, rate of, this is being cut in half, right? So rate of decay. So these would all use the original equation. So this again would use original. I just want to know how many years would it take to have 30. So I would now set this equation equal to 30. So once you get your exponential equation, you're either plugging a number in for t or setting the equation equal to it to find the time. And again, then it's just like Algebra 2 pre-calc solving this. And this comes out to be 2,762 years. And if it asks for the rate of growth, that's when you're going to use the differential equation with the derivative.